So when we move beyond simple linear regression to multiple linear regression with 2 inputs, and then we move on to multiple linear regression with 3, 4, 5, 6 inputs, it can be difficult to visualize beyond 2 inputs. But conceptually, it's the same, right? So multiple linear regression, it's just like simple linear regression, except instead of a line, we fit an n-dimensional, what we call hyperplane, in an n+1 dimensional space, with n referring here to the number of inputs on the right-hand side of the equation. For example, with x1 and x2, right, as inputs into our multiple linear regression model, we're fitting a plane of 2 dimensions, defined by that base of that 3D scatter plot, in a 3-dimensional space. Okay? So consider this. In simple linear regression, right, you have one input variable, and you're fitting a line of 1 dimension in a 2-dimensional scatter plot. With 2 inputs, you're fitting a plane of 2 dimensions in a 3-dimensional space. Here's where it gets a little tricky. Right? With 3 input variables, with x1, x2, and x3 as predictors or inputs in our regression model, what you're really doing is you're fitting what we call a hyperplane of 3 dimensions in a 4-dimensional space. And you can just keep going. Now, 4 dimensions, it's pretty difficult to visualize. I certainly can't do it. But the great thing is you don't need to. Right? As long as you understand what's going on with simple linear regression and multiple linear regression, intuitively it's the same process. You're just kind of moving into different regions of more dimensions. But intuitively it's just the same. Right? You're just fitting what we call a hyperplane through this cloud of data. So let's look at this, okay? Just to make this tractable and tangible. So here's multiple linear regression with k equals 3 inputs. Right? Here we have the point estimates, the coefficients. We have an intercept, we have a slope for father's height, a partial regression coefficient, we have a slope for mother's height, and then we have a slope for family size. So what we're saying is we're going to predict the height of children, right, using not just height on the parents, mother and father separately, but we're also going to check out larger families. Maybe larger families have taller children, or maybe smaller families have taller children. Who knows? We're going to use that as an additional input in our regression model. So our regression model has the following form. The y-hats are a function of an intercept plus 3 different coefficients. So the intercept is 24.4. So the intercept is the value when x1, x2, and x3 equals 0. So we say when you have a father of 0 inches, a mother of 0 inches, and when you have no people in your family, then the model predicts the height of a child is going to be 24.4 inches. Now again, that is not a sensible interpretation because everybody has a family of some size. Right? They at least have 2 parents, and well, in this case, we would suppose they at least have 1 child. At least the person in the data set is a member of his or her own family. So nobody has a family of 0. And then, of course, people have parents of some height or another. But the basic idea is the same. The intercept is simply giving that value when x1, x2, and x3 are equal to 0. Then we also have these 3 partial regression coefficients. So we say that for every 1-inch increase of father's height, right, we expect children's height to increase by 0.36 inches, holding constant the other inputs or variables in the model. To put it another way, holding constant mother's height and family size. The partial regression coefficient for mother is interpreted as follows. For every 1-inch increase in mother's height, we expect children's height to increase by 0.28 inches, holding constant father's height and family size. And then finally, when we look at family size, we'd interpret it as follows. For every 1-inch increase, for every 1 person increase in family size, for each additional family member you have in your family, we'd expect the height of children to decrease by 0.11 inches, holding constant mother's height and father's height. Okay. Again, family size is interpreted as follows. For every additional family member you have in your family, we expect that children's height will decrease by 0.11 inches, holding constant the other inputs and variables in the model. Let's look at another example. Here we're going to predict calories in breakfast cereals. Right? So this is a really pretty common sort of analysis done by nutritional epidemiologists. They're often interested in obesity, and a big social factor related to the cause of obesity is simply caloric intake. So we might look at breakfast cereals. Breakfast cereals, at least in the United States, were quite popular in the 80s and early 90s. They've since decreased in popularity, but they tend to be pretty caloric. So you might consider what predicts the number of calories in a sample of breakfast cereals. So here's a data set of breakfast cereals. We have all these different kinds of breakfast cereals. The sample size is 30. And then we have these different characteristics of these cereals. We have the calories, we have grams of fat, and so on and so forth. So the idea is we're going to fit a multiple linear regression model. We're going to predict the number of calories in these different cereals using fat, sodium, sugars, and protein, all measured in grams as inputs in a multiple linear regression model. So this is what a regression model looks like. You can see that we have these full set of estimates. All right, so we have an intercept, and slopes for all of these. And what we see here is that we can construct a single model using these estimates, but we can also look at the t-values and the standard errors and the p-values to interpret the coefficients. Assuming that this is a random sample from a population of cereals, we can make a conclusion. In particular, we find that the amount of fat, sugar, and protein in breakfast cereals, they're all statistically significant predictors of the overall caloric intake at the alpha 0.01 level. You can see that sodium is not a statistically significant predictor of the amount of calories in cereal, which makes sense because sodium is not particularly caloric. So we can see here that we can make some conclusions based on these multiple characteristics of these different cereals.